So please hold on, students. We are trying to streamline the lecture on the YouTube. So we have some technical issues here. We'll soon start the class. Please just give us some minutes. Thank you.
It's on YouTube already, ma.
Okay.
You can start, ma.
So we are back and the class starts now. So this is Fsc112 and my name is Dr. Cudwekeze. I'm a chemistry lecturer and I'll be taking you on the aspects of electronic energy levels and orbitals, where we'll be discussing the general rules for assigning electrons to atomic orbitals and all of that. Because we've wasted some time, let's just go straight to today's class. Now, we already know that from our elementary chemistry, we are told that an atom is composed of protons and neutrons, and these protons and neutrons are found in the nucleus. Also, atoms, the nucleus is being surrounded by electrons. And so in excess, what describes an atom is the proton, the neutron, and the electrons. While the protons and the neutrons reside in the nucleus and they are immobile, that means that they do not move. The electrons revolve around the nucleus. And so because of the movement of electrons around the nucleus, it's usually not easy for us to locate the exact position of electrons in the nucleus. So it's usually not possible to locate the precise location or the precise position of an electron within an atom. But we must define a place for the electron in the atom. And so the idea of probability came into existence. So instead of saying that this is a particular place that electron will be located in an atom, scientists prefer to use the word the probability. That is, the probability of finding an electron in a particular place is what is being used. Now, the most probable pathway that an electron is likely to be moved is what we determine. And this pathway is what we call the orbitals. You know, over the years, it's been called orbits. So orbital and orbits are actually the same thing. Now, these orbitals, like we say, they are actually contained in the energy level. I'm trying to move this. So you have the orbitals that they are arranged according to the amount of energy that the electrons of that orbital is composed of. And so these are what we refer to as the energy levels. The energy levels starts from the electrons accommodated close to the nucleus, and it extends to the electrons further away from the nucleus. If we look at this schematic diagram, this is the electronic energy levels and orbitals of sodium. In here is your sodium as an atom, the one in the nucleus, where you have the protons and the neutrons of the sodium. Now, the sodium is being surrounded by an electron residing in the nucleus. So each of this energy level, this is energy level 1, N1, you have 2 electrons accommodated there. We are still going to elaborate on this when we go further. But I just want to show us what we mean when we say energy levels. So the orbitals is where you have your electrons, and you determine where your orbital is depending on the amount of energy being obtained by the electrons in that orbital. This is more explanatory in this slide. Like I said, the energy levels are being designated by the letter L, N, small letter n. So when we have n equal to 1, we are actually considering the first energy level. And this first energy level has the 1s orbital in it. So where you find the 1s orbital is in energy level 1. This 1s orbital with the electrons there will reside in this energy level 1. Now we move on to the next energy level. So sorry about that. So we move on to the second energy level. The second energy level, N is equal to 2. The second energy level has in it the 2s and 2p orbitals. So you could see that when we go further away from the nucleus, we have more orbitals in each of the energy level, further away from the nucleus. Let's go back to the previous slide. Sorry. Okay. Now, if we go back to this previous slide, remember what we are doing is we want to arrange our orbitals in the energy level. And we are arranging these orbitals in the energy level according to the amount of energy that electrons in these orbitals are composed of. So the higher the energy that the electrons are composed of, the further away the energy level will be from the nucleus. That is exactly what is happening here. For n is equal to 2, the amount of electrons that will be accommodated in n equal to 2 will be higher or greater than the amount of electrons accommodated in energy level 1. Hence, the energy level 2 will be the distance of the energy level 2 will be far away from the nucleus. And that also applies to energy level 3. For energy level 3, we have 3 orbitals here. We have the s orbital, the p orbital, and a d orbital. And so electrons that are accommodated in the 3s, the 3p, and the 3d orbitals will be residing here in energy level 3. And you can see the energy level 3 will have more. It will have more electrons than the electrons in the energy level 2. Now let's go further to n equal to 4. For n is equal to 4, this implies that we are in the 4th energy level. 4 means that we are in the 4th energy level. Now let's look at the orbitals that we will find here. The orbitals that we will find here are the orbitals that have electrons in the 4s, the 4p, the 4d, and the 4f orbitals. So the electrons here will find themselves in this 4th energy level. And again, the number of electrons here will be greater or higher than the number of electrons found in energy level 3. Now I have, before we go into that, let us make use of this particular scheme because it's very, very interesting. Now, let's start with n equal to 1. For n equal to 1, the shell is composed of just one orbital. If you look at this, this is showing us the orbital. All these circles is composed of just one orbital. This red colored ball is one orbital. And now what it's telling us is this, that it has one orbital here. For n equal to 2, n equal to 2 is composed of two orbitals, the 2s and the 2p orbitals. That is what we have for n equal to 2. So n equal to 2 has 2 orbitals, 2s and 2p. But remember, the 2p orbital here, if you look at this ball, the 2p orbital is broken down into some other orbitals, which is 3 orbitals of the same energy. If you see, the purple balls are aligned on the same energy level, and so they have equivalent energy. What this means is that for this n equal to 2 shell, that you have 3 subshells of 2p orbitals and 1 subshell of 2s orbital. So in all, you have 1, 2, 3, 4. You have 4 subshells for n equal to 2. Now, this is how you calculate till you get to n equal to 4. Now, let's go to the next slide. We have been talking about s orbital, we've been talking about p orbital here, and we're talking about d orbital. That is the orbital that we find in each of these energy levels. Let us describe what these orbitals are. This is an s orbital. I think it is more explanatory here. The s orbital is the orbital that is spherically symmetrical. What it means is this, that it does not have any direction. If you look at this, you have it in a circular form, just one circle. So it's not going any, and there is no direction for particular atom in the nucleus. It is spherical, it is spherically symmetric about the atom's nucleus. Now, for this particular orbital becomes higher in energy as the number of n increases. And so, for one s orbital, you could see the size of one n orbital because we are describing this size in terms of energy. You want to use it to show how the energy increases. For one s orbital, look at the energy. The energy is as small as this. So as the n increases, going from 1 to 2, n is increasing. There's going to be an increase in this s orbital. This is because we are actually increasing the distance from the nucleus. That is, whatever you have, like we saw in the first scheme, that as the number of n increases, the electrons are further away from the nucleus. And so the s orbitals will increase. Now for 3s orbital, that is the 3s orbital, you could see that the 3s orbital is bigger than the 2s orbital, while the 2s orbital is bigger than the 1s orbital. And these sizes are listed in this order: 1s, 2s, 3s, 4s, and so on and so forth. Now, the next orbital we want to look at is the p orbital. Now, not every electron will reside in the 1s orbital because as the number of electrons increases, we know from our elementary chemistry that the s orbital, each orbital will accommodate a maximum of 2 electrons. So as we move away from, as the number of electrons increases, that is in terms of increase in atomic number, it then means that we need another orbital that electron will reside in. And so that's the next electron after, the next orbital after the s orbital is the p orbital. Now, for the p orbital is found at the second energy level. Remember that in the second energy level, we have access to 2 orbitals. That is the 2s orbital and the 2p orbital. And again, remember I've told you that for the p orbital, there are 3 equivalent p orbitals that are present there. So These three equivalent orbitals are what we have here as we'll be moving this because I'm making use of it. We have the three equivalent d orbitals with the symbols, the px, the py, and the pz. These symbols are assigned randomly depending on the direction that on the point where you have the direction of the orbital. Now, subsequent levels that also have the p orbital are also they also have these symbols. What do I mean? For the n equal to 3, electrons that are going into the third energy level will be accommodated in the 3s, the 3p, and the 3d orbitals. And so the 3p orbitals again have symbols 3px, 3py, and 3pz. So for every p orbital, there is px, py, and pz, representing the three equivalent p orbitals. Now we look at the d orbital. The d orbital again is an orbital at the higher energy level. That is the d orbital. Again, electrons that are going into the third, fourth, and from the third energy level, they have been accommodated in the d orbital. Now, at the third energy level, we have, in addition to the 3s and 3p, the 3d orbital. If we go back to the first scheme that we looked at, we notice that we have 5 equivalent d orbitals. These five equivalent d orbitals are orbitals of the d with the same energy level. That means that they are equivalent, just like that of the 3p orbitals are equivalent. And so we have the 3d xy, 3d xz, 3d yz, 3d x squared minus y squared, and 3d z squared. Now, for the 3d orbitals, we actually categorize these orbitals into 2. We have the 3 first orbitals, those lying in the xy plane, the xz plane, and the yz plane. And those are the ones that we have as 3dxy, that is the dxy, the dxz, and the dyz. Now we have the next category comprising of 2 orbitals. Remember, the orbital is made up of 5 degenerate orbitals, which is categorized into 2. The first one is those lying in the xy plane, that is your dxy, lying in the xz plane, that is your dxz, and the other one lying in the yz plane, that is your dyz orbital. Now, the second category under the d orbital is the dx squared minus y squared and the dz squared. These ones, they are pointing towards x and y axis. And so we have them classified together. They are classified as a group, dx squared minus y squared and dz squared. So that is what makes up the 5 degenerate orbitals. Now, the fourth orbital that we want to look at, which is of higher energy, is the f orbital. For the f orbital has a complicated shape, and so all we need to know is this. We should just remember that there are 7 f orbitals in each level, and f orbital starts from energy level 4. The f orbital starts from the energy level 4. So as we go on from 4, 5, 6, and so on energy levels, you have f orbitals in those energy levels. Now, I want to ask a question, and you can go to the chat and put your answer. I want you to tell me we have energy level 1 to 4. That is n equal to 1 till 4. For each of the energy level, I want you to categorize or tell me the type or the different orbitals that we have in each of them. The different orbitals that we have in n equal to 1. You can go to question and answer and put down your answer, or you put it on the chat box. Nobody is answering me. I'm not talking about last week. Oh. Please, for energy level 1, that is n equal to 1, what type of orbital? Good. N equal to 1, we have the s orbital. Someone has answered me, Victor Olubukola. For n equal to 2, we have what? For n equal to 2, we have S and P. Good. For n equal to 2, you have S and P. Somebody says P. No. For n equal to 2, we have 2 orbitals, S and P. Correct. Kind, I can see you. Tolu, I can see you've answered everything. N equal to 3, S, P, and G. Correct. Okolo Daniel, I can see you for n equal to 3, 3P and G. Good. That means you guys are following the class. So let's go on. And for all of you that answered my questions, I have a gift for you at the end of the class. You can come to my office and just get a small gift while we go on with the class. Now we understand what we mean when we say energy level and orbital. At least we can differentiate that. Now, the next thing I want us to look at . Now, I want us to look at this, the energy levels of orbitals. I want us to look at the energy levels of orbitals. Remember that the first picture that we looked at, the 2s and the 2p orbital, they were placed on the same energy level as if they have the same energy. That is just because we just started there. So we just want us to take it step by step so that you will understand the class. Now, we need to look at the energy levels of these orbitals because that is what we are going to use when we want to start filling in electrons in the orbitals. What I mean is this. Just like you have your house where you live, when you start taking in visitors, you know where to place your VIPs, you know where to place your relatives, and so on and so forth. We have categories for this. That is what we want to do now. We want to look at the energy level so that when electrons are coming in, we know where to move that. We will know where that electrons will go, where it will be accommodated. Is it going to be accommodated in the 1s? Is it going, in the 2s or the 2p? Because the 2s and the 2p are in the same energy level, they have the same number of n. That does not mean they have the same energy. No, they have the same number of n, but they have different energies. Now, this picture shows, I think it's very clear. Let's start with n equal to 1. For n equal to 1, we just have one orbital, and that makes it easier for us. So electrons here will just be accommodated in the s orbital, and that is just the 2 electrons. It will accommodate maximum of 2 electrons. Now, when we have an atom that has more than 2 electrons in it, that is, has an atomic number of, say, 3, that means that once the 1s electron takes up, once the 1s orbital takes up 1 electron, this will now move. Another electron will be accommodated in the 2s orbital before the 2d. And I don't want to stress it here because we are going to look at how to fill electronic configuration. When we get there, we'll discuss in detail what we mean by all of these things, but let's just take a preamble of it. Now, the 2s orbital will take electron before it moves, before electrons start going into the 2p orbital. The 2s orbital again will take maximum of 2 electrons. Each orbital takes maximum of 2 electrons. So for the 2p, for the p orbital, when n is equal to 2, that is 2 orbital. Remember, we have 3 orbitals of the same energy level. And so when electrons start coming here, because they are of the same energy level. It's just like in your class, you are on the same, you are in the same class. Now I am teaching all of you together. You're in the same energy level. It's not as if I'll teach some class and after I'll teach the other class. And so whatever I am saying is binding on all of you. I have to exhaust it. Even if I want to do an extra class, it has to be later, not now. And so for this p orbital, when electrons start moving in here, electrons will move in each of the orbital singly. Though we said each orbital will contain maximum of 2 electrons, but because these orbitals are degenerate, they will take electrons singly before they will start taking the second one. Now for n equal to 3, remember we have s, p, and d orbitals. S, p, and d orbitals. S orbital, we know it's just 2 electrons. Now when we move to 3p orbitals, the same thing that happens to the 2p, the 3 degenerate p orbitals will take electrons singly and so on and so forth. Now when we move to the 3d orbital, the 3 orbital has 5 degenerate orbitals. And so electrons will be accommodated, they are singly before it starts pairing. We are going to look at that. The same for 4s to 4f and 5s to 5g and so on and so forth. Now I have a diagram here. It's just a recap of what we'll see later. Now when you're writing the electronic configuration in terms of the electronic orbitals, you write the one that is the energy level. This signifies the energy level. You have the orbital. The orbital is just telling you the subshell, and you have the number of electrons in the subshell. Now, for n equal to 1, your subshell is equal to 1. And what I always tell students is this. Because what we want to look at now is we want to put together the energy levels, the number of orbitals, and the subshells. We've talked about energy levels, that is n, from 1 to 4, and so on and so forth. We talked about orbitals, the s, the p, and the d, and the subshell. That is what we want to bring together now. And now know what values do we assign to all of these things? How do we put them together and make up something meaningful? Now let's go. We are going to take it a step at a time. Let's start from the s orbital. The s orbital will contain 1 subshell. It will have 1 subshell. And so for n equal to 1, you have 1 orbital and 1 subshell. Now listen to me. Remember, s is 1s, subshell is 1. Please, if you have your notes, can you just help me? Draw something like a table. Draw a table. You have, just say energy level. In brackets, put n. Then put subshell in the other one. Now we've done n equal to 1, isn't it? N equal to 1, the orbital is s, and the number of subshell is what? 1. Now let's move to n equal to 2. For n equal to 2, there are 2 orbitals, the s and the p orbital. Good. Now the 2s orbital will have 1 orbital, which is just the s, and 1 shell, because it's just the s. 1 shell and 1 orbital. Now the 2p orbital will have 3 orbitals and 1 subshell. 3 orbitals and 1 subshell. Now the 3 orbitals here plus this 1 orbital is going to give us 4 orbitals. The 1 shell here and the 1 shell here is going to give us 2 subshells. Now again, let's go back to our notes and write. For n equal to 2, you have how many number of subshells? You have 2 subshells. You have 2 subshells. And now we are going to include in that our table number of orbitals. Number of orbitals. I want to start with n equal to 2 to explain this so you'll understand it better. For n equal to 2, the number of energy level is, n equal to 2, sorry. The number of subshell is 2, and the number of orbitals is how many? It's 4. You know how we got the 4. 1 s orbital and 3 p orbitals. I think let's go and use this. It's going to be better for us. Okay, can you see this? For n equal to 2, you have how many subshell? You have your 1 and you have your 1. That is 2 subshells. Now, but you have how many orbitals? 1, 2, 3, 4. So for n equal to 2, there are 2 subshells and 4 orbitals. Now let's go to n equal to 3. For n equal to 3, you have 1, 2, 3. You have 3 subshells for n equal to 3. You have 3 subshells and you have how many orbitals? Let's count. This is 1, 2, 3, 4, 5, 6, 7, 8, 9. You have 9 orbitals for n equal to 3. So you have 9 orbitals for n equal to 3 and you have 9 subshells. Now listen to me. The summary of this is for any number of your principal energy level, it corresponds to your number of subshells. If you have first energy level 1, you have 1 subshell. For energy level 2, you have 2 subshells. For energy level 3, you have 3 subshells. For energy level 4, you have 4 subshells. For energy level 5, you have 5 subshells, and so on and so forth. Now, what the term is the number equivalent or degenerate orbitals. For the number of orbitals for n equal to 3, you have 1 coming from the s orbital plus the 3p degenerate orbital plus the d degenerate orbital, making 1 plus 3 plus 5, giving us what? 9 orbitals. For n equal to 4, you have 4 subshells, the s, the 4p, the 4d, and the 4f. But let's see how many number of orbitals that we have. We have 1 plus 3 plus 5 plus 7. So 1 plus 3 plus 5 plus 7 is going to give us 16 orbitals. So for n equal to 4, there are 16 orbitals. I just hope you guys got this because we'll be making use of it later. Now I have a question here, a classwork, which please let us quickly answer it on the chat. Let's go back to our chart. Let's go to the chart. Put in your answers. How many orbitals and subshells are found within the principal shell n equal to 4? Tell me, do not just write the value, because if you write the value without telling me that it's for orbital, I will not know. How many orbitals for n equal to 4? How many orbitals do you have? How many subshells do you have? Quickly, I'm going to the chart now. Good. Akinde Ezekiel, I have you. Adioyen, Joseph, good. 416, good. 16, okay, 16 orbital, 4 shell, good. Good. Now I have the second question. We have more than 2 questions there. How many subshells are possible for n equal to 3? What are they? How many subshells are possible for n equal to 3? What are they? You have 2 questions. For n equal to 3, how many subshells? Can someone give the answer to number 3? For n equal to 3, good. 3 subshells. What are the subshells? Good. 3s, 3p, and 3d. I saw some of you writing SPD. No, because you already have n equal to 3 here. You must signify that they are 3s, 3p, because you know that you can have 4s, 4p, and 4d. So do not just write sp and d. Do not just write sp and 3. Can somebody attend to question number 3? How many subshells are possible for n equal to 5, and what are they? What are they? N equal to 5. Omo, Carol, I can see you. Emmanuel, I can see you. I'm seeing all of you. N equal to 5, 5 subshells. Ferdinand, you didn't give us the what are they? What are they? Okay, you did not give us good. What are they? I didn't ask you to give us the number of orbitals. I said, what are the subshells for n equal to 5? Good, good. 5s, p, d, f, and g. Good. Correct. 5s, 5p, 5d, 5s, and 5g. I can see you, Oka, correct. Solomon, you're correct. Who is this? Kingston, Adenike, Richard, you're correct. Mary, I can see you. Correct. Ojako Chioma, you're correct. Okay, let's go on. We'll still come back. We have many questions to answer. This class is actually going to be a practical class. We'll be doing more of question and answer. And anybody that answers my question, you stand to gain something, even as the gifts are small, but it's something that you value. Now let's go back to let's have a recap of the class you had with Dr. Nejo on quantum numbers. But in this case, we want to use these quantum numbers to describe electronic orbitals. We want to use the quantum numbers in describing the electronic orbitals. Now, always remember, when we're talking about electronic orbitals, we are looking at actually electrons, because it is electrons that reside there. Remember, it is a place where there is probability of finding an electron. That is our definition, so you should not forget that. Now, each electron in an atom has 4 quantum numbers that can describe it. This is what you did in last class. It's just a recap for better understanding. The first one is the principal quantum number, which is designated as small letter n, the principal quantum number, which is designated as small letter n. And in your last class, you were told that this principal quantum number describes the energy level on which the orbitals reside. So all those n equal to 1, n equal to 2, n equal to 3, and n equal to 4 that we've been talking all along, they are representing the principal, they're actually the principal quantum number. Now, remember, our interest or our objective in this class is for us to use all of those quantum numbers, the 4 quantum numbers, to describe an electron. Now, the second one is the azimuthal quantum number, which is designated as italicized letter L. This one describes the shape or the size of the electron. And we are told that the values depend on the value of n. So if n equal to 1, L equals to n minus 1. So L is going to be 0. And again, there's a range for your L. L ranges from minus L to plus L. I always tell students is minus L, comma 0 to plus L. Now, like we say, the second quantum number, which is your azimuthal quantum number, it describes the shape of the space of the region in which the electron occupies. If you can have a recap of what we just did when we are looking at the electron, the orbitals, you could see that each of the orbitals has its own shape. The s orbital has a spherical shape. The d orbital has its own. The p orbital has, and so on and so forth. So what this quantum number describes is actually the subshell. For the s orbital, L is equals to 0. Because for s orbital, you have 1 minus 1. Remember, we said it's from 0 to n minus 1, which is going to give you 0. The p, for p orbital, you have electrons. Electrons start getting into p when you have n equal to 2. Remember, let's go back so that it won't be as if we are saying it offhand, I mean. For n equal to 2, that's where your p starts. There is no p in n equal to 1. So for n equal to 2, you have your p. For n equal to 3, you have your g. For n equal to 4, you have your f. So let's go to where we are now. So for p, the subshell is going to be 2 minus 1, which is 1. For d, it's going to be 3 minus 1, which is 2. For f, the subshell is going to be 4 minus 1, which is 3. So this is what we are going to use in describing the electrons. Don't worry about all these numbers. You get to know what we mean when we start using them and how to use them to describe an electron in an atom. Now, the other one is your magnetic quantum number, M subscript L. It describes the orientation of the region in space occupied by an electron with respect to an applied magnetic field. I'm not going into explaining all of these things because Dr. Nejo did justice to that. This one ranges from minus L to L. This means that L depends on N, while ML depends on L. If you can get that, L, which is your azimuthal quantum number, depends on the value of N, while your magnetic quantum number, M subscript L, depends on the value of L. So you see how it goes. Very simple. Now, the last but not the least is your spin quantum number. This one has only two allowed values, the plus half and the minus half. Now, for today's class, we're not going to make use of this, but I will explain it just briefly. But when we'll be writing our electronic configuration, we will get to use it more. So let's go through using the four quantum numbers to describe electron in an atom. Now you have, I used 1s here and 2s here. The only difference between these two is the the n. Here n is equal to 1 for 1s and n is equal to 2 for 2s. For n equal to 1, your L is equal to 0, and this represents S sub shell, which means that L is equal to 0. And so you will just have one orbital. This is this value that is giving the orbital, please. It is this 0 that is showing, because 0 is counted when you're counting the number of orbitals using the magnetic quantum number. You include number 0 in counting the number of orbitals that you have. All these things we have done before, but we just want to use the quantum number to describe them. Now, this is your 1s orbital electrons. It will accommodate maximum of 2 electrons. And so the magnetic spin quantum number describes it that you have 2 allowed spins, the plus half and the minus half. It is the direction of these electrons that is giving them plus and minus. This going upwards, direction going upwards is the plus half, direction coming back downwards is the minus half. We are still going to deal with this later in subsequent classes. Now, for any NS subshell, even if it is 3s, your azimuthal, that is your L, is going to be 0, and your ML is going to be 0. So it will have one orbital, and it's going to have 2 s orbital electrons. That is 2 electrons. So your 3s will have 2 electrons. Your 4s orbital will accommodate a maximum of 2 electrons. Your 5s will accommodate maximum of 2 electrons. Here I said note, it is only the value of n that differs. The energy level, it is okay. What I'm saying is this. It is only the value of n, that is the energy level, that differs. What all these quantum numbers does not differ when you're using them to describe an electron for any particular n value. Even if its n is equal to 2, 2p, 3p, 4p, 5p, they will have the same quantum number, the same type of quantum number describing each of them. Now, we are going to have our hands on this. I'm going to do this with you together. We have 11 minutes. I'm going to do this with you together. So please have your hands on the chat box. Have your hands on the chat box. It's a classwork, but I want to use it to explain what I said earlier in using the 4 quantum numbers to describe the number of to the electrons in an atom. Now, this one says, what value of L corresponds to a d subshell. What value of L corresponds to a d subshell? L here is the azimuthal quantum number. So what value of L corresponds to d subshell? Can I have my answer in the chart? Remember, we say that for n equal to 1, L equal to 0, and here you have your s orbital. For n equal to 2, L equal to 1, and that represents the p orbital. For n equal to 3, L equal to what? Because this is where you have your d orbital. It is n equal to 3 that gives the d orbital. What value of L corresponds to a d subshell? So I want to check the chart box. Who said 3? Who said 3? Who said 3? Who said 3? We are taking the questions one at a time. What value of L corresponds to a d subshell? It is 2, please. The person that said I, it is 2. Because for the value of L, the value of L is equals to n minus 1. The value of L is equals to n minus 1. And you know that your d orbital starts when n is equal to 3. So 3 minus 1 is going to give you what? 2. So the answer is 2. Okunubi, thank you. Then the second question says, how many orbitals are in this subshell? How many orbitals are in this subshell? I'm taking the second question. So anything you're putting down there, please, can you put in orbital so that I will know that it's different from the value of L. Somebody said 3 orbitals. Somebody said 16 orbitals. Not which of the questions? Let's take these questions one at a time so that I will know how well you understand this. You have L equal to, L is 2, that is the answer. How many orbitals are in this subshell? How many orbitals are in this subshell? Okay, I can see that some of us are not getting it. So let's quickly, but a lot of you are getting it, so I'm happy. But let's quickly go to, what did I do? Okay. I hope this thing is not telling us to. What is happening? Sorry, I'm coming. What happened? Okay, just hold on. Just hold on. I'm trying to get. Can you still see the screen? Because I think I've done something here. Can you can see my screen? Okay. If you can see my screen, let me see how it goes. Just a few minutes left, so I have to be fast. This is not what I want, please. Oh. No. Okay. Don't worry, if you can see me, let me go to explain what we mean. That is what I'm trying to do, but it's not coming up. It's not coming up, so it's really... Okay, don't worry yourself. Let's not waste our time. I can talk. I can always explain. Now we have said the diagram that I gave you, that energy level that we have circles. That when n is equal to 3, that's where you have 3s, 3p, and 3d orbitals, isn't it? Good. And so the d orbital, that is where electrons start moving into the d orbital. Now the question says, what is the value of L corresponding to d orbital? Remember that for your azimuthal quantum number, that L is equals to 0 to n minus 1. What this means is that is when you're considering all the 3s, 3p, and the 3d. But for you to get your L is equals to n minus 1. So here our n is equal to, I've done that too. I've done that. I've done all of those things. Don't worry, you guys should just calm down. I don't know. Sangu. For n equals to, here, n is equal to 3. So our L azimuthal quantum number is going to be 3 minus 1, which is equals to 2. Do we get that? So our L is equal to 2. Now, Ajike Tomilola, d orbital has 9. It has 9 orbitals, not 3. I'm going to explain. What you have in there is your L. Your L is equals to Can someone correct me? Can someone correct me? Good. Then for the orbital is what? How many orbitals? 9 orbitals. Let's see if it is 9. So we are going from -2, -1, 0, +2, +1. That is for L equal to 2. But Ajike, remember that for that particular n equal to 3, it's not only the d orbital that you have there. You have 3s, you have 3p, and you have your 3d. The 3s is going to be 0, which is 1 value. The 3p is going to be -1, 0, +1. And the 3d is going to be -2, -1, 0, +1, +2. So let's count all those numbers now that we have. We are counting them as values. Do you understand? So 0 is 1, -1 is 2. I've counted the one of 3s. I have 1 orbital there. If I go to 3p, I have 3 orbitals. -1, 0, +1, I'll write 3. So 3s is 1 orbital. 3p is 3 orbitals. 1 + 1 is 4 orbitals, isn't it? Now, for the 3d, I have -2, 1, -1, 1, 0, 1, +1, +2, +1, +2. So I have 1, 2, 3, 4, 5. I have 5 orbitals. So 4 + 5 is what? 4 + 5, exactly. You have 3 subshells, but you have 9 orbitals. Because each of the subshell has its own orbital. The 3s is a subshell. It has 1 orbital. The 3p is a subshell. It has 3 orbitals. The 3d is a subshell. It has 5 orbitals. So 1 + 3 + 5 is going to give us what? 9 orbitals. So for L equal to, for values that correspond to L, the value of L that corresponds to D is equals to 2. And the number of orbitals, because you're talking about the orbitals that you have there, the number of orbitals for that particular energy level is 9. Now, let me tell us something. If I say 3D, maybe 3D5, if I just say 3D5 now, okay, the next class we'll take it. Let us just go with what we have now. So that, how to get, okay, Ugochukwu, can you listen to me? How to get the magnetic, the ML. Now let's go back to this to this question that we asked now. Let's go back to these questions that we asked now. Don't even put the orientations of the P, but let's go back. Ugochukwu, if you can listen to me, we've said that for L, for our d orbital, L is equals to 2, isn't it? And if L is equal to 2, that means that your N equals to 3. Because L equals to N minus 1. So 2 equals to N minus 1, N equals to 2 plus 1, which is 3. Are we together? N equals to 3. Now, go back to the, okay, I'm not even going back. When we have our energy level, under N equals to 3, you have 3S, you have 3P, and you have 3D. Are you with me, Ugochukwu? Good. You have 3S, 3P, and 3D. These 3S, 3P, and 3D, we call them subshells. These are the subshells. So under N equals to 3, we have 3 subshells. Are you with me? Good. Now, when we now go to the orbitals, when we go to orbitals, each subshell will have its orbital. Now, for the 3S, for every S orbital, there is only, for all the S subshell, there is 1 orbital. For P subshell, you have 3 degenerate orbitals. For these subshells, you have 5 degenerate orbitals. Now let's go back again, Ugochukwu, to what we have. So if we say that for any S orbital, there is 1, for any S subshell, there is 1 orbital. For any P subshell, there is 3 orbitals. For any D subshell, there is 5 orbitals. Now let's go back, Ugochukwu. Now for 3S, how many orbitals will you have there? You'll be answering me now, fast. For 3S, how many orbitals? My time is off. 1, good. For 3P, how many orbitals? For 3P, how many orbitals? 3, good. For 3D, how many orbitals? For 3, good, 5. Now add up the 3. 1 plus 3 plus 5 is what? 1 plus 3 plus 5 is what? I've not seen Ugochukwu's answer. 1 plus 3 plus 5, fast. 9 orbitals, good. Now, let me go to explain how we use them for the ML, that is the magnetic quantum number. Listen, let's go back again, Ugochukwu. You'll be the one answering these questions now. We already said that for S subshell, that our L equal to 0. For P subshell, L equal to what? 1. For this subshell, L equal to 2. Are you with me? For S subshell, L, which is azimuthal, is equals to 0. For P, L is equals to 1. For D, L is equals to 2. But remember that we have the magnetic quantum number, ML, describing each of these things from minus L to plus L. Not just the number, but from minus to plus. So let's go to S, where you have L equal to 0. Is there anything like minus 0? There's nothing like minus 0. So we still have 0 there for the ML. So for S, for the subshell S, L equals to 0, ML is equals to 0. Good. Now let's go to our P. For P equal to L, L is what? 1. So you're going to have minus 1. And after minus 1 is 0, before plus 1. Do you understand it now? Minus 1, 0, plus 1. That is what we mean by P. Because we already discussed that for the P subshell, our azimuthal quantum number is 1. So ml is going to be minus 1, 0, plus 1, because ml is equal to minus L, 2, plus L. If you can understand that, can you please say it on the platform? Good. Now let's go to D. For the D subshell, L equal to what? 2. But remember, ml is minus L to plus L. So we are going to be going from minus 2 to plus 2. So it's going to be minus 2, minus 1, 0, plus 1, plus 2. Minus 2, minus 1, 0, plus 1, plus 2. Good. Exactly. Now we'll go to, for all these subshells now that we've done. Now let us count the magnetic, count the ml. You will see that it is the ml that is telling you the number of orbitals. Let's count the ml. Under S, we have 1 ml, which is 0, isn't it? That is 1. Then under P, you have how many L? Minus 1, 0, plus 1, 3. Good. 3. Then under D, you have how many ml? 5. Minus 2, minus 1, 0, plus 1, plus 2, 5. Good. So 1 plus 3 plus 5 is what? Is 9. So it is the ml that actually, because ml is dependent on what? L. L is your subshell. ml will not tell you the number of orbitals in that subshell. Did you get that? Say a big yes so that I will know my time is up. It's 7:10. Good. So that will be all for today. Now, on Wednesday, we are still going to start with this. But I'm going to start with the questions. So you should get ready for my questions. And I'm going to give you a question that you will use to, describe. I'll give you an electron in an atom. And I want you to use this quantum numbers that we've used today to describe them. I don't want somebody that will be giving me wrong answer. If you give me wrong answer, I know your name. Oluwafemi, my diploma building upstairs. You see my name on my door. Thank you so much. See you guys on Wednesday. Bye. And please read, study, so that on Wednesday we'll be faster than today. Bye for now. Tell me bye now on the chat. What did I do to you people now? It's better now. Good. Bye. I'm happy. Bye. See you on Wednesday. I can't.